Section 417 is called separately excited generator under load. Mainly what we've done up to this point is look at the generator under no load conditions. Now, we're going to connect a load to this generator, and we're going to see some changes that occur internally, and we will notice those changes that happen internally based on what we observe at the output. So let's walk through that and see what that looks like. And we're building our level of base knowledge on electrical machines, and now we're going to bring it up to another concept here, which is this idea of something that we call voltage regulation. In the figure that we're looking at now, titled Separately Excited Generator Under Load, we go back to the first excitation scheme where we had a separate standalone device that was providing the excitation for the armature, providing the flux for the voltage to be generated, in other words. And so we're going to start with that. And it's the reason is, you know, again, we don't see this scheme too much, except when we get into very large generators, like you might see in a power plant or something. Then we actually see this situation with those. But for this, we're trying to get a different concept. So, you know, we're simplifying this a little bit in terms of the excitation to get this other concept. And what is different now is we have connected to this DC generator a load. Now these loads can be all types of loads, you know, they're not always resistive loads, but in this case, it's showing a resistive load. And so up to this point, you know, before we, you know, connected a load, you know, we saw that the voltage that was produced at the armature was the same as the terminal voltage. But what we're going to see now is this thing that occurs when we connect a load. And, you know, in the last segment, we talked about this R sub O, which is the conductor and interpole conductor resistance. And so what happens when we connect a load and current starts to flow through this circuit, then if there's a resistance here, we know that voltage is equal to current times resistance. And so we're going to get a voltage drop across that. Now think about that. So, you know, we looked at this situation where let's say we develop 120 volts across our armature at no load, right? And you know, we got that from, you know, this equation. All right, so we got this voltage, but now we connect a load to it, current starts to flow, and we're going to drop some voltage across this internal resistance, this R sub O. So let's say that this is 120 volts, and let's say that this is 1 ohm of total resistance. So, you know, if we had 120 volts, you know, and let's just say for simplicity's sake, let's say that there's 1 amp of current that's flowing in this. It's basically a series circuit, isn't it? So if I have an amp across an ohm, then that would mean I would drop 1 volt across this resistance, and the output voltage would be 120 minus 1, or 119 volts. That's what the load would actually see, less than the armature voltage. Okay, so, you know, there's a representation of that. So what does that look like? You know, picture this or look at this. Let me clean it up a little bit before we move to another slide. But, you know, here's our situation. Current starts to flow. We drop a voltage across here. There's a voltage drop here. And then what we're looking at is, an output voltage available to the load that is less than that is generated on the armature. So the way we account for that would be this, what's called a load characteristic of this separately excited generator. And we'll see different characteristics based on different types of generators, but this one is for a separately excited generator. All right, now, the voltage that we're referencing, looking at this figure 424, is the voltage that we see here and here, okay? So here's our schematic representation. And so here is that voltage, E sub 1, 2. And then we see as, for instance, we get the current that's flowing through the circuit. And we'll pick this one here on the graph of 5 amps. Okay, so at 5 amps, here's our curve. At no load, it was 100 volts. But at 5 amps, if we look onto the voltage between 1 and 2, he says that now we're looking at 95 volts. So the drop from 100 to 95 occurred across R sub 0. And we dropped 5 volts across there because we had 5 amps of current. If we continue and we get to 10 amps of current, then we go from 100 volts to 90 volts, okay? So we drop 10 volts across there. So what we're seeing is this situation where the greater the load, the greater the load current, the greater the voltage drop that occurs internally into the machine. And what we're going to see is the characteristics of that drop will vary based on the type of field connection that we have. This one is specific to a separately excited generator.